back at it again. Back at it again. Where were we? We were here trying to find the boundaries of this guy. With cylindrical integration, and we're saying, let's open up get cylindrical integration Khan Academy. I think that was the link that I found interesting, at least the most interesting, and it was exactly here, right? So here, the volume of a sphere. The hard part is putting the bounds on the integral. However, doing this with cylindrical coordinates much easier than with the critical coordinates, but the R will just leave within the unit disk, which is very natural to describe in polar coordinates. Yeah, so here we exactly. The bounds of Z will depend on the value of R. Yeah, because it's the that's fine. If we look at yeah, and in our case it's a similar thing, right? Because the again the function, right? This was this so given a specific radius, you kind of have like you have a value that's the same for all of them, for all of these radiuses, and so that's kind of your Z value. The Z value, which is defined by the equation itself, is what, if you look at the sort of from a profile perspective, the Z value kind of goes like this, right? So the Z really, we only care about the Z value here, which is always positive. And in this case, we know it's always going to be, 0 is going to be at the bottom, because you're never going to get like a negative Z. Are we? This is our expression, right? So if we go to Desmos calculator, graphing calculator, and so R is X, and then we add a slider for A, and that's always going to be like this. Doesn't matter, like for negative A's, it's also, the Z is always positive, doesn't matter. The Z is always positive. Now, what is that Z? Well, in this case, it is actually bound by this expression, right? The R, it's going to depend on R and alpha. So it is going to be, I mean, here I put in these, that is really what Z is going to be. Between 0 and these. But I'm not so sure about the baseline here. I'm not so sure about these part. I think this is going to be right, because Z is always going to be between 0 and these. That's you know, that is our Z, so to say, right? It's a function of R and A. But then what is it that we are integrating? What should I put in here? That is what bothers me. And why am I putting these here? Right? Yeah, these here. So what should I put in here? Why just S2? That just makes no sense. Since the bounds of Z will depend on the value of R, we'll let the innermost integral handle Z while the outer writing down, because this is okay, because this is the, so this is a more generic form. Now the question is, I'm almost thinking like that actually these boundaries are, this is then valid for everything. I don't know if, moreover, this tool is powerful enough to do more than just find the volume of the sphere. For example, you could integrate a 3-variable function inside the sphere. That is the thing. Maybe that is just the way these works, which is like the hard part of finding the bounds is no different, but the computation of the integrals done by it will change. Because here you're keeping the same bounds. Maybe that's, yeah, maybe that is the way. What if we just do it like this then? Does this work? Or how? So here's another example. But here you'll find different boundaries. Okay, so let's follow. So what is this example? A wedge-shaped region over a region which looks kind of like a slanted pie slice. The problem with this region might be described using the following list of properties. Blah, blah, blah. This time you'll not just be finding the volume of this region. Instead, our task is to integrate the following 3-variable function. Okay, so you have this function inside this region. This might seem out of place in an article about integrating in cylindrical coordinates, since everything here is given in Cartesian coordinates. Indeed, you could set up the triple integral using Cartesian coordinates. The expression shows the function as well in description of bounds. This suggests some rotational symmetry and the z-axis, which cylindrical coordinates are well suited for. For example, look at the range of our x and y values. Describing these with a pair of integrals is a real pain. However, polar coordinates becomes very simple. This means the bounds on the integrals handling will be constant, so you can't do better than that. What are the criteria such as describing polar coordinates involves the property blue. The bounds on z can be translated to these. Okay, so putting this together, our triple integral looks like this. Okay, so okay, so I think I've been framing these incorrectly. Now I'm getting a bit. So you're defining a region. The bounds are then mapped to that region, and then you integrate a function inside that region. Notice how simple the bounds are. If you're up for a little pain, you can try finding the appropriate triple integral bounds. Now you can write that. So now you can write the function f using polar coordinates. And of course, we incorporate the main takeaway of this article, which is how to write dv in polar coordinates. So dv is these. Putting all this together, we get our triple integral and its final solvable state. Okay, yes, but I don't get one thing, so I'm not so sure I get this. So these bound, so what is the function we're integrating? This is the function we're integrating. We're not finding the volume of the region, instead is to integrate the following 3-variable function. But why I can't just do that in first. Let's see what this gives us. So if I use these and I just plug in here, like, let's see if that works. Okay, so we have our function, and then I'm gonna say this is minus square root of 1 minus r. So yeah, 1 minus r squared. Okay, and then this is square root of 1 minus r squared as well. What's the point of, like, you can just always then have an arbitrary region. You could always just, okay, because this is the unit. I get it, because this is the unit because this is the unit circle. That is the point. You define the region. So you probably have to define the region big enough so that you're okay. Because this is for the unit sphere. Okay, so this means that here, you know, you would be integrating over, like, if you kind of had like a sphere here, so just that little part here. Okay, I mean, let's try it, see what happens. So z, so essentially, okay, so this is the region. I get it. Okay, so and then the function times these. Okay, so this is definitely S01 times these. Okay, that makes sense. And these are, what is this? This is nothing. So Z is between these two guys. And then what happens now if we say Python x2 scope 1a? What do we get now? So now this is the function we're integrating, and yeah, it's kind of the region we're integrating is the unit sphere. That's taking, awesome, empty. The fuck? That's stupid. That's stupid. It's definitely stupid. Well, we know it's 0 here, so we could even make it easier because we know it's positive, so it could just be the half sphere, right? Kind of have that, you know. I don't know if that makes it easier, but square root of r squared, and then no, okay, cool, sorry, that's wrong. Then here I have to stick to 0, 1 because it's the unit sphere what we're doing. Yeah, that's my bad. That is wrong. Like, it, you know, the boundaries have to stay these boundaries, 0, 1 and 0, 2 pi. I just have to define a better region, I guess, but this would be, I mean, that should give me something, which is not exactly the solution, right? But it should definitely not be empty. That's the problem. And why is it taking so long? The question is, why would then just multiplying actually give me the integration of that function in that region? You know what I mean? why would multiplying these times these and then doing that, it is actually giving me the integration of this function. It's taking its time. Might never finish. Hopefully not. Here, I guess, kind of, yeah, it depends on what is the value of a, right? Because for smaller values of a close to 0, it goes quite crazy, because here is definitely 1, so the sphere would not be that bad of an approximation, to be honest, because as we go to a's that are, you know, above 1, like that actually is, you know, it's just those small, like when a, and I guess when a equals 0, 0.5, yeah, it almost feels like it would, the sphere of volume 1 actually would, it seems to be a good approximation, but it's still running. Could I how could I just do this by hand? Integrate with respect to z. It almost feels like that should make it easier. That should be relatively easy. Why is it taking that long? And R (0 to 1). That's also not correct, right? I mean, yeah, okay, if we, that's the radius of the sphere. Because essentially for any value that is bigger than 1, we're really getting close to 0. So, and then 2 pi. So using the inverse chain rule, we can quickly scribble down some notes to see what this antiderivative is. Definitely not gonna dive too much into this going on with our integral then. Yeah. The volume of the unit sphere. It's multiplication intersection. I guess that's a good question, because I think that's probably what it almost feels like intuitively should be like, oh, look at this, so we have something which is crap. No. Okay, but we got something. We got something. Yeah. what if we just use n01? I mean, that defines already our region, right? So if we do these, what do we get? Something funkier, faster though, but definitely too crazy. Definitely too crazy. It's like I'm thinking, why can't we just use any coordinates? I mean, these any boundaries. It's like at this point I'm like, oh god, that's just the rotation of this. Why? Done by either you or a computer will change. Yeah, I mean, why? I don't get it. I just don't get why you can't use the same function as just the boundary. You know what I mean? I don't understand why you just can't use the same function. Why you have to do this times the dv. Okay, I guess because the same function is like infinite, right? So you can't just, you got to define a region around it. But then I guess these are like, you can define whatever you want. I mean, yeah, like it doesn't have to be, you know, that's the point that I'm trying to make, is like, I know that it's gonna have this cone shape thing. So for a given a, right, let's say a2, it's gonna look like this. So it just always kind of goes up to infinity. But it approximates to infinity. It's gonna be like this to infinity, and it's gonna, and then what? That's the z values, right? And so they just go up to infinity. And here 1, right? Really. So essentially here what you will have is that the, okay, but here you're gonna have then a funkier shape, because what this is telling you is that for, well, it can be, like the smallest is for a radius of 0, there's going to be like 1, right? And then as the radius grows, say for this point here, for all these points here, then you're going to have let's say z value that is like a little lower than these. So you're gonna go like these. Then for a z value that's like these, an r value that's like these, because we're in 2D space, that you're gonna have a z that is like lower than these, and there's gonna be almost kind of, it's gonna look like a cone kind of thing. But z is always gonna have this shape. It's just in a way symmetric around the z-axis, right? And then it's going to be just 1, because you can never go, it's not going to go to infinity, it goes to 1. So the z is really actually capped at 1. I don't understand why I can't just say z goes from 0 to 1. Why I can't say it just like this? That should work. But then it just doesn't. It definitely doesn't. R can go to infinity. Z goes between 0 and 1. That's the boundary. R can go really to infinity, from 0 to infinity. And then the rest is 2 pi. These boundary conditions, like, yeah, okay, but it's not exactly like that, right? Any value, like z is really constrained by these kind of, by the function itself. That's the volume, like, this is also something that should work. And that just doesn't give a better answer. Oh God. Doesn't give a better answer. What if we say n is real? Does this change anything? No, it just takes some of the things there. It takes the absolute values away and stuff like this. Yeah. A is real. R is positive. R is positive. This is real and positive. Yeah, I don't know. I truly don't know how to get. At that point, I'm like ultra stuck. I don't really understand. Well, but then, okay, so what I'm basically saying is then this should just really be, you know, it's the volume we're calculating here. So that should just be 1. But then that also doesn't give me a good answer. It's funny because it actually gives me the same as in the top version of that, which is good. should be able to validate these though. Because I should basically be able to say, you know, I mean, that is, if I integrate this function, so if I integrate check, so if I integrate basically S01, now if I integrate, yeah, so if I integrate basically square root of 2 times absolute value of a divided by square root of pi and squared times, so if I'm integrating these, okay, so this thing squared times S01, and I'm integrating it from, what am I doing? So yeah, basically I should kind of do the same. I should just basically do, this is S check is this expression, and now I should just do the same thing here, but just say integrate S check the volume of these, so these and then S check and print S3. What does this give me? Oh, that was definitely apps A. Yeah, 1. I mean, of course, right? Maybe it is the question, maybe the question it is here is like how do we, yeah, 3D space, cylindrical integration 3D space, maybe that is really what I'm kind of missing here. So, you know, like hyper cylindrical integration, what is the, well, it's not cylindrical anymore then, quasi-polar coordinates and sphere. Spherical coordinates. because spherical coordinates like these do take me, so this kind of works now. And then if we go back to these, so we have these things here, right? So A01 is this stuff. So spherical coordinates, Khan Academy. So here we had the spherical coordinates thing, yeah, exactly, sinus. So the trick here is finding then the R values, right? So it almost feels like zero pi, 0 2 pi, and then 0 3. What is this 3? As the R, okay? Yeah. So let's take these form. So this is 0. The first integral is 0 to infinite. The second is 0 to pi, and then 0 to 2 pi. 0 to pi, and then 0 to 2 pi. Okay. And I think that was giving me 0 as well. Oh no, okay, not bad. Not bad. It's 3. Not bad. It's this is, so the solution to that was because that's the thing, maybe I just have to take it to, you know, three dimensions, right? This is 2 dimensions, so I just maybe have to take it to, this is a solution. Maybe I have to take it to n-sphere integration. And exactly, this is maybe where I have to take it. And this is where it's interesting. So it seems like it's 0 to 2 pi. Zero to pi and 0 to 1. For all other I. 0 pi for all other I. Okay. So you're kind of folding, because here's a bit different. So this would be, so let's keep these. So definitely we need phi 2. So so this is basically what this is saying is 1. So n is 3, right? So we're 4 dimensions, so 4 minus 1 is 3. So this would be, first it would be yeah, first that's cool. Although here they start first with the angles, then they do dr, and then they do d theta 1. First, hyperspheral coordinates, we use the coordinate system, and then 4, and it's 4, so theta, so okay, so actually we should basically have phi so n is 4, so phi 3, this will be phi 1, and then we have phi 2 and phi 3, exactly. So let's put it like this. And so this is phi 3. And so we say basically that we start with integrating here. Sort of first we integrate, so first is r, so this is r times 3, then phi 1, then phi 1, phi 2. Okay, so we do so it's 3, and then sinus of phi 1 squared, and then we do times r2 sinus of phi 2, yeah, okay, exactly, phi 2, yeah, and then this, so and that's it, yeah, and then there's dr d phi 1, dr d phi 1. So the first d, okay, so dr d phi 1 and then d up. Okay, so we start from d1 and then, yeah, so we start from r, that's correct, so that's fine. We start from r, so this is s2, so we start from r, and we say s1 times s01 times s02, and then we start from r, and then we start from phi 1, and phi 1 is phi 1, the last one is 2 pi, phi 1 is, okay, so we start from phi 1, then we do phi 2, and there's also 0 pi, and then we do phi 3, which is 0 to 2 pi, and then we do these, and then we print these. I think this is correct. So this is r to the power of 3, and then phi 1, r to the power of 2, and then phi 2, right? So that's yeah, it's not phi 1 and you go phi 2. Exactly, and then we start with the R, and then we start with this. Let's see. Does this work? Fuck. No, not exactly. Okay. 2 pi, so it's 0 to pi, it's phi 2, phi 3. S1, here we take S2, here we take S3. No, but there's something wrong. The first thing we do is it's definitely not, it's weird because it's not 2 pi, and then that's definitely weird. There's something off in here with these, but okay, it's got to be like that. Just things make sense. It's got to be. I have to explore these generals. It has to be like these. It just definitely has to be like these. But yeah. To me, this seems pretty complicated for the kind of exercise. Yeah, but maybe it is what it is. Generalized to 3 dimensions. It's got to be like, it's got to be something like that. I'm getting, you know, I mean, with 2 dimensions, I'm getting a pretty similar result. So that gives me hope. It just now, I think I have to figure out these. Still giving a bit of rounds, but what else can we do? I somehow, I don't know. I'm gonna get through this even if it takes me the whole fucking year. Bye.